Okay, I think we should get started. I think people will stream in as we get started. So good afternoon, everyone, and welcome back to this week's iteration of our AI4OPT seminar, and which is again going to be virtual. So we have Chi Jin with us here today from Princeton, and Chi Jin is an assistant professor in EC at Princeton. He got his PhD from UC Berkeley, working with Professor Michael Jordan, who is also incidentally visiting us next week. Chi's research mainly focuses on theoretical machine learning, non-convex optimization, and reinforcement learning. His work on proving the efficiency of Q-learning is quite famous. His other work includes proving that noisy gradient descent escapes saddle points and so on. And for many years, anytime somebody mentions POMDPs, my immediate reaction is POMDPs are scary. I don't want to deal with them. So I can't wait to hear Chi Jin talk about why or when POMDPs are not scary. The floor is yours.
Thanks for the introduction, and thanks for the very good introduction about the topics as well, motivating why we want to do this partially observable reinforcement learning, not scary thing. Sorry, my voice is a little bit low because I'm having a bit of cold, and I really wish I could visit in person because my health issues, so I kind of have to do this virtual thing. As introduced, I'm Chi Jin from Princeton University, and today I'm going to talk about our recent progress on partially observable reinforcement learning. First, I would like to thank for all our collaborators. So our results are actually coming from a lot of thoughts and discussions over years, and I'll contribute a lot of them. Credits are given to my wonderful collaborators, and they are Qinghua Liu, Alan Chuan from Princeton University, Sham Kakade from Harvard, Akshay Krishnamurthy from Microsoft Research New York, and Priest Natrapalli from Microsoft India, and finally Csaba from University of Alberta, and also DeepMind. So we talk about partially observable today. So I think most of you are familiar. If you're familiar with reinforcement learning, you know nowadays most people are talking about reinforcement learning using the model of a Markov decision process. And in a fully observable setting. However, a lot of practical problems are so-called partially observable, in the sense we don't have full information of underlying states. For example, when we play this poker game, the underlying states should be the cards on both my opponent's hand and also on my hands, and also the cards on the desk. However, whatever the cards on my opponent's hands are hidden from me, so it's partially observable. As for this robot, for example, it has a first-person camera, so it can only see whatever happens before him, and it cannot see what behind him, or it cannot also not see whatever was occluded behind some obstacles. And similarly, it also happens for some strategic games like StarCraft, and also this hide and seek, where when we have the simulator, we hard code it so that each agent can only see the things in front of him. Okay, basically, partially observable thing is ubiquitous everywhere in the modern reinforcement learning. And so today, I'm going to talk about some theoretical work on the reinforcement learning. So when we talk about theory of reinforcement learning with partial observability, the first thing is what kind of model we are talking about. So we will mostly focus on this model called partially observable Markov decision process. So it is a standard Markov decision process which have state and action, but each state will further generate some observations. And in this POMDP, we assume only observations are known to the learning agents, and those states are hidden from the players, so we cannot see these underlying states. Okay, so we can have two viewpoints of this POMDP. One is we can think it's a Markov decision process with some emission. The other thing is we can also ignore this action. We just have a state and observation. This is just a standard hidden Markov model. And now we add in a control to it. So you can think POMDP is harder than both MDP and HMM. So it's kind of a merge of those two models. And very importantly, in the POMDP, if we don't know the states, the observations are no longer Markovian. So a lot of things break up. Okay, so there are a lot of unique challenges when we talk about POMDPs to make it like classically or in the past decades, we always believe like POMDPs are hard. For example, when we talk about a fully observable scenario, like let's say tabular MDP as an example, we kind of like, tabular MDP has a finite number of states, finite number of action, finite number of horizon. And we also, there are a long line of research which we try to understand the computational and statistical complexity in learning those MDPs. And it turns out we can say the computational complexity and some complexity are all polynomial in number of states, and number of action and horizon. So basically we can say we can learn it efficiently in terms of polynomial. Of course, there are a lot of detailed rates, but in the high level, we say, oh, those problems are learnable and we efficiently learnable. However, when we go beyond to the POMDP, and even the easiest, the tabular POMDP, which again, we assume we have finite number of states, action, horizon, and also finite number of observations, it becomes immediately a lot more challenging because, as I said, in the POMDP, the observations are no longer Markovian. So we have to reason about the states, and we no longer see the states. So we have to reason about the states based on our observation. And so this, we usually call it as a belief over states, because we can say, okay, based on my current observation, I say I have 1/2 probability in this states, 1/2 probability in that states. So I'm not very sure, but I can guess like what is the probability in each states. In order to reason about this belief over states, typically we need to maintain some memories. So we should not look at only the observation in the current step. We also need to look at observation in the all previous step. For example, when we play poker games, whether my player bluff or like whether my player like basically whatever the player did in the previous like whether he raised high or whatever, the entire history gonna say something about what is possibly like the cards in their hands. So that's why we need to maintain the entire memory, and the memory is possibly is very, very long. So because we consider episodicity, the entire horizon is H. So the entire possible histories would be something exponential in the number of in the length of this each game. And then we will deal with all these challenges while exploring the environment. So this is why make the tabular, even a tabular POMDP very challenging and leads to a lot of classical hardness results. And we will say a little bit more about what is hardness results. So first thing is computational hardness. And we can say the planning itself is already hard. So what planning means? Planning means like in a POMDP, we need to assume we have some transition and some emission. So we have underlying models. Planning just says, even if I already tells you what is model, so you don't need to learn, you don't need to do any learning at all. You just need to use this model to compute what is the optimal policy. This is easily done in the MDP by using Bellman equation. However, in the POMDP, you can say finding this optimal policy is actually p-space complete. The biggest reason is, I said, the history has exponential possibilities. So basically, you need to like basically enumerate all the possible histories, and which make it p-space complete. And you may wonder, okay, my policy, optimal policy might be difficult. I might just want to consider a restricted class of policy. The restrictive class so that my policy would only consider the current observation. So it's memoryless policy. I only want to compete with the best memoryless policy. Even this is NP hard. So basically none of them can be done in polynomial time. The second thing is the statistical hardness. So even if I allow you an infinite computation, like I give you some supercomputer that is able to compute whatever, anything in just 1 second, learning POMDP still require some exponential number in the length of samples. We will actually see the counterexample, like why it is hard later in this talk. It's quite intuitive. So because of those two reasons, like both computational hardness and statistical hardness, for a very long time, like for 40 years, like since POMDP has been proposed, people just believe these models are just hard. It's unlike MDP, we can provide a lot of efficient learning results. POMDP is just hard, like we cannot do anything. And so that's why we should not study this normal model. And this has been like basically the thought for the field like for so long. And today we will actually provide a first line of results which address the statistical efficiency. Okay, so we will not handle computational efficiency today, but we will handle the statistical efficiency about the POMDP problem. Okay. Of course, the way we handle the problem is not like we say, okay, we can just directly prove some polynomial sample results that will contradict with this hardness results. It's just not possible. So a better way to do this is like we should look at those counterexamples, hardness instance, like why these are hard. And we see like, are they hard because of some artificial reason, or are they hard because in practice this is just hard? So we will actually identify those hard results. Hard instances are hard because some very trivial reason POMDP included some example, which of course we cannot learn in polynomial samples. But in practice, a lot of problems we face, like when we play poker or play like this robot thing, will not be those hard instances in worst case. So our strategy would be, we want to identify some rich structure or rich subclass of POMDPs so that it can be statistically tractable. Hopefully this class will be very large so that it will include a lot of practical problems we care for partial observability. And the second step is, once we identify this big subclass, we will design some efficient algorithm so that we can learn this rich class sample efficiently. Okay, so this will be the main question and the two main goals of the talk today. So the talk is 1 hour. So to avoid you get completely lost in the later parts, I will just quickly get an overview of our results and we will go into details later. So remember, we have two questions. One is about problem structure, the other one is about algorithm. So in the problem structure, we will identify a new rich subclass of POMDP we call the weakly revealing POMDPs. We will talk about what are the hard instances, and essentially this rich subclass is basically just ruling out those pathological POMDPs which basically you cannot learn sample efficiently. And those pathological POMDPs are those POMDPs basically observation doesn't tell you anything about the underlying states. Remember, we call it partially observable because we hope it will reveal some partial information, but the model actually includes some examples which doesn't tell you any information about the states. So as long as we rule out those kind of instances, we can learn it. We can make it tractable. And the second part is the algorithm. We will actually introduce a very simple generic algorithm. It's called optimistic maximum likelihood. As the name suggests, it's just a combination of two parts. One is optimism for exploration. The other one is this classical maximum likelihood estimation. It turns out this simple algorithm is good enough to learn this weakly revealing POMDPs. Okay, and you're gonna learn this any weakly revealing POMDPs in polynomial samples. So this is the overview of our results. And I want to emphasize that significance is provide the first line of sample efficient results for learning from interactions for large class of POMDPs. Any questions so far before we jump into the details? Okay, if no questions, so we'll go to the formal formulations. Okay, as we said, the POMDP is basically can be viewed as a MDP with emission. So the formal formulation is like a little bit more complicated than MDP, where it's similar to standard MDP. We have set of states, finite set of states, finite set of action. For this talk, I will just focus on the tabular setting, where we assume everything is finite. And what's more is we have an observation set. Basically, we have a set of observations we have. And the standard T will use it as a transition, which is says underlying transition of this Markov decision process. It's like, what is the probability of the next state S prime conditional on my current state S and action A? So this is a transition probability. It's the same as MDP. But what's more is we have an emission probability, which tells you what is the probability over observing some O conditional I'm currently on state S. Okay. And also have some initial distribution over S1. So the reward here, we will assume, for simplicity, we just assume reward is containing observation. So we can see it. So basically reward is a function which will map observation to some 0, 1. Okay. So we assume this to avoid some information leakage. For example, I have some additional information from the reward instead of observation, to just make things simple. And the horizon, we assume this is like episodic setting. So the entire one episode will end in H steps. So basically, for example, a game is only has 100 steps long or 10 steps long. So it always ends in H step. Okay. So this is just standard, as a standard MDP, the only thing more is we have observation set and we have an emission set. And then let's define the policy and values. So a little bit different from the standard MDP where you can define a policy as a map from the states to action. Here we need to define a map, the policy to be a map from history to action. Okay. So it's very important here, the policy need to depend on the entire history because the observation is no longer Markovian, as I said. So in general, the observation, the policy will take into an argument, take into an entire history up to step H, which is O1, observation at first step, action at first step, then observation at second step, action at the second step, until the observation at H step. It will take into account of entire history and then make a single decision, like make an action, like tells you what action you're going to play at this round. This is policy. Okay. And then we will define the value. And because this policy is more complicated, it no longer just depends on current states, it depends on the entire history. So we will no longer define some like intermediate value of the intermediate states or something. It's just not defined. So we'll just define the value of always start from the initial states. So this is a total expected reward received under some policy pi, starting from the very beginning. Okay. So value only have one argument, that is policy. For each policy, we have a value. Okay. Good about this part. So the objective is become very simple. Is we just want to find an optimal policy so that we should maximize the PV pi. Yeah, because we assume we have always have the same initial states. So this V pi basically is start from initial states. So we're gonna have the maximum value. Okay.
A quick clarification question.
Yeah. Yes, please.
Does this value would depend on the initial value, V pi? Is it a vector or a scalar?
It's just a single value. Like we assume we have, it's a scalar. We assume we have initial distribution over states.
Oh, okay.
Basically,
okay.
it's an expectation over the initial states.
Okay. Yes. Thanks.
That's a very good question. Yeah. Yeah. And also, I just want to mention some details. Like the policy, also we say is a collection of map for each step because we allow a different step to have different policy. And actually, the input for different steps is also different. Like the length of the history is different. So the policy is like different for each steps.
So okay. Just like the MDP, the initial distribution doesn't matter when you maximize V pi, because MDP, if you maximize for one
MDP
state,
doesn't matter, right?
Yeah. Okay. Also for this one, the initial distribution matters.
That's why initial distribution matters.
Okay. Okay.
Yeah, POMDP is very different. Initial distribution will actually affect the entire like estimation about the underlying states, so it matters a lot.
Okay. Okay. Thanks.
Okay. Very good. Okay. I just want to say a little bit more about the settings. So, what is the interaction protocols? Like what is the setting we're gonna learn? So we just assume we have some online interaction with the POMDP. So we're in this reinforcement learning setting, online learning setting. So we don't assume like we have some collected samples. We kind of like we say all the samples we need to collect by ourselves by interacting with the POMDP environment. So we say at each episode K, we just do two things. One is agent will just pick a policy to execute. This policy can be anything, can depend on the previous episodes. And then we will just execute this policy and receive a trajectory O1, A1, O2, A2 till OH. This is all we observed. And then we will repeat this process to like capital K episodes or whatever. And we decide what is the optimal policy. Okay, so this is what we call learning from interaction, because all the samples are collected by the learning agents. It's collected in some online fashion. Okay, so there are several components about the learning. One is we said there are some planning parts. Even in the very end, like we already know what are the model, what are the transition, what are the emissions, and all what are the values. We need to compute what is the optimal policy. This is the planning part. And of course, we don't really know what are the models, what are the values. So we need to do some model estimation. We need to use the collected data samples to estimate what are the models and values. This is the estimation part. And then finally, as I said, we don't even have collected data, so we need to collect by ourselves. So this is why we need to do this exploration versus exploitation trade-off, so that we can strategically collect some more informed data samples to make us learn better models and have better policies in planning. Okay. And I just want to emphasize a little bit about our work, distinguished from prior works. I think the condition we're gonna identify is also subsumed in some of the work, but in addition, they assume a lot of additional strong assumptions like ergodicity or something like they can try to visit all the states or whatever. And so like reachability, invertibility of potential matrix ergodicity. So they don't deal with exploration challenge. And also I think the results are not that clean. Okay. Good. Okay, so this is a basic setup. So let's go to the first question about our problem structure. Like what class of POMDP, like why the POMDP in the worst case are not efficiently learnable? And what are the class of subclass of POMDP, which is if tractable? So the first thing, as I promised, that we should look at the hard instance. The hard instance is turned out to be POMDP, although it's partially observable, but it's actually unobservable without observations. So what does it mean is we can consider the following examples. In order to specify a POMDP, we just specify an underlying MDP and then the emission. So in this case, emission is always a dummy. So we say dummy observation is basically no matter what it states, I will just give you the same observation. So that this observation doesn't tell you anything about whether I'm in state 1 or state 2 or whatever. So it doesn't say anything. So it's a dummy observation. And underlying MDP is this so-called combinatorial log. It's also a classical example which I've been having used in this exploration scenario. So it is an MDP with only two states. And it is a very special MDP so that S0 is a very special state. There's only one way to get to S0 in the very last step. It's like you take A star, A star, A star, A star, and you go to S0. And whatever other actions you take, you will go to S1. And whenever you go to S1, it is absorbing states. So it's just always staying S1. It never goes out. Okay. And of course, I can slightly generalize this combinatorial log so that I make this action to be different. So I need to put in a specific action sequence like A1 star, A2 star, A3 star, AH star, so that again ends up in this S0. Otherwise, I will always end up in S1. And I will make the reward so that I only gonna receive one reward if I reach the S0 in the very last step. Otherwise, I will just get 0 reward. Okay. So you can think this problem is basically equivalent to entering a passcode. So there is an optimal policy, which just forget about all the observations. I don't care about the observation. I will just always input this fixed action sequence, which will always give me a cumulative reward of 1. However, because I have dummy observation, so I have no idea which underlying state is. So if I just make this everything black, this is basically like entering a passcode. If I get the correct passcode, I get reward 1. Otherwise, I get reward 0. So in order to find the right passcode, unavoidably, we have to pay A to the H samples. There's just no way we can get around it. Okay. But any question with this hard instance? Okay. But on the other hand, we can expect in a lot of practical scenarios, we are not facing this worst case scenario. So our observation is not like this dummy observation, it doesn't tell you anything. Our observation is somehow informative. For example, when we, in the first viewer camera of robot, it will tell you something information about the underlying states. So we basically can conclude the difficult part only happens if there are two states, or in general, two mixture of states that will lead to the same distribution over observation, so that I have absolutely no idea to tell which states I'm in. Okay, I cannot even tell like whether I'm more likely to in this one or that one. So I have to have a little bit distinguishment between these two states, so that we can at least guess like I'm with higher probability in this state or with higher probability in that state. Okay, So the strategy to define a new subclass is basically we just want to rule out this pathological instance where we have no observation. We prevent efficient learning. So how to prevent this, how to get rid of this pathological instance? We look at this emission. Emission is like recall emission is a probability of observation given states. We can write this emission as an emission matrix, which is an O by S matrix. Okay, and each entry is, as I said, is a probability of observation given states. We conclude if there are two states that will lead to the same distribution over observation, then it will become hard. So one immediate way to get rid of this thing is we say any different mixture of states will induce different distribution over observations. This way we get rid of this hard instance. Okay, so what we say is if we have two distribution over states, let's say mu1 and mu2, where mu1, for example, is 1/3 probability in state 1, 2/3 probability in state 2, while mu2 is 1/2 probability in state 1, 1/2 probability in state 2. So those are two distribution over states. If mu1 is not equal to mu2, then the observation distribution induced by this two-state distribution will also be different. So basically OH applied on mu1 will be also different than OH applied on mu2. We just require this observation distribution to be different. Okay, and mathematically you can say this is also equivalent to say this rank of OH need to be rank S. Need to be essentially a 4-column rank. This is what we call observability or weakly revealing. Of course, when we want to add this finite sample guarantees, we cannot just say it's like a rank equal to S because it can be infinitely close to some low rank main matrix where we cannot use any property. So basically our assumption is just a robust version of this rank of emission being rank S. So what we're saying is this is our only condition, that is alpha weakly revealing condition. We say is the S singular value of this emission matrix is lower bounded by something that is away from Z0. Okay. It's just a robust version of this. And it turns out this is the only assumption we make in this paper. Okay, so basically this assumption identifies a subclass which we call weakly revealing POMDPs. And this is only single assumptions we have. Okay. So for people who are like very familiar with the main matrix, it will immediately spot a problem. Like it says this S singular value of emission is greater than 0. This is only possible if this matrix is a tall matrix. In the sense, we have number of observation is greater than number of states. However, there are a lot of scenarios of POMDP where we have a very little amount of observation, but a very high amount of states. Okay, so this is called overcompleted POMDP setting. While when S is smaller than O is called undercomplete. So previous definition only apply to undercompleted POMDPs. So how are we going to handle this overcompleted setting? Like for example, we only have two observations, but we have 10 states. So the way we do it is we use multiple steps of observations to distinguish step instead of just one single observation. Here we say the different state distribution will lead to different observation distribution in one single step. Now we say we're going to use multiple steps to do it. So the way we do it is we can define a so-called M-step emission action main matrix. It's a matrix no longer O by S, but A to the M, O to the M by S. Okay, so each entry of this matrix is a condition on current state being S, and I'm taking this action sequence and what is the probability of observing certain observation trajectories. Okay, so this is basically you can think it's a multi-step version of emission matrix. And similarly, we just assume the S singular value of this multi-step matrix to be lower bounded by some constant, so that we can avoid this undercomplete issue by looking at some multiple step observation in the future. Okay, these are the conditions we identified so far. Any questions? Okay, so now we have a large class of POMDPs, and it seems very reasonable because we're just getting rid of those examples which is completely non-informative. Observation is completely non-informative. And now we say observation needs to reveal a little bit about the states. Okay, and so now to come to talk about the algorithms. And algorithms, we kind of like also struggle a little bit in the beginning, and turns out it's kind of like also quite different from the standard MDP algorithms for the observable setting. Because prior algorithm, most algorithm for the observable setting is a value-based algorithm. Like we do value iteration or we do Q learning. Most important thing is we estimate this Q value. But the important POMDP, as I said, the optimal policy will depend on the entire history. So that means if we want to define some intermediate value in the like step H or step H-1, the value will no longer just have a one single state as input. It will have an entire history as input. So that means this value has exponential size. And if you want to learn this complete value, that will take exponential number of samples, which is, again, inefficient. So what are we going to do instead? Is we actually going to do model-based approach. That is, we're going to estimate the transition and emission. Remember, although the policy or value will depend on the entire history, but the transition is just a single-step transition. Emission is always a single-step emission. So transition and emission only have polynomial number of parameters. Like transition has S²A parameters, emission has OS parameters. That means learning the model itself will not incur any exponential size. So this is like basically a key perspective. And this is also the key reason why you can see a lot of existing currently algorithms for learning POMDP are always model-based. So in our first work with Akshay, Sham, and Qinghua, we actually designed a spectral-based algorithm like tensor decomposition, matrix factorization to estimate model. And this algorithm is basically borrows from, like adapted from similar algorithms which learn hidden Markov model, like to estimate a model, and then we can use that to like find the optimal policy. So in today's talk, we will actually introduce an algorithm we introduced later in the work with Qinghua, Csaba, and Alan. And we actually say we can just do an even more simpler algorithm or from some first principle. That is, we just do maximum likelihood and optimism. Once we just combine both of them, and we're good, we can find an optimal policy. Okay, so what is the algorithm? To introduce the algorithm, well, let's first introduce a bit of the notations. So when we will just use theta to denote the model parameters. Remember, in the POMDP, the most important model parameters are just two things. One is T, which is transition probability. The second one is O, that is emission probability. And we have transition and emission at each step. So we just collectively call all the parameters as a theta, which is model parameter. And then we use this notation V pi of theta denote the value of policy pi if my true model is specified as parameter theta. Okay. So those two notations. Then the algorithm is actually quite simple. It only have three major steps. So as the name suggests, I will always maintain a confidence set over the models. So we have a set over models, which is transition and emission. So the first step is optimistic planning. That I look at my confidence set B, and I will just find the optimistic model and policy within my confidence set so that it maximizes this V pi theta. Okay. It's similar to UCB kind of idea. I find the best arm, and here I find the best model in my confidence set, which maximizes this value. Okay, and this pi is called optimistic policy. Once we have this optimistic policy, we just execute this optimistic policy to collect a trajectory that is O1, A1, O2, A2 till OH. And then once we have this trajectory, we will use this trajectory to update my confidence set. So it's just three simple steps, optimistic planning, which find the optimal policy, and then just execute this optimistic policy. And then finally, we use it to update my confidence set. Okay. So as you can see, the first and second step are pretty straightforward. So the only third step is like the non-trivial step. And we'll see a little bit more how we update this confidence set. This is why MLE comes in. Okay, so because we have a model parameter, so we can compute the log likelihood of each model of the trajectory, of the path trajectory under these models. Okay. And we can take the maximization over models. Basically, this computes the MLE estimate. So this tells me what is the maximum likelihood that can be achieved under my my model class. And my confidence set I will just maintain those models so that the log likelihood can be slightly smaller than MLE, but it can be not too small. It can be only smaller than MLE by a small tolerance beta. So you can think this is a robust version of MLE. MLE gives you a point estimate, which is a single mode model, which achieves the maximum likelihood. And here I'm just achieve all the models. I'm allow all the models the likelihood can be slightly lower than this maximum value by some statistical tolerance. Okay. And this is some notation. Basically, in high level, you just want to know this is how we construct the confidence set. Okay. So once we have this algorithm, then it just becomes very simple. We can get these guarantees. So we say for any alpha weakly revealing POMDPs, our OME algorithm is able to output an epsilon optimal policy within this polynomial episodes, where polynomial is in the horizon, in number of states, number of action, number of observation, and also the tolerance of the policy, and also this alpha weakly revealing parameter, where the singular value is lower bounded by alpha. Okay, so we say a single weakly reading conditions allows us to learn everything in polynomial episodes. And this is for the under-complete setting. For the over-complete setting, we say we can also have the M-step weakly reading POMDPs, and where we can use an M-step version of OMLE. The only difference is like here in the data collection steps, we are no longer just executing the optimistic policy. We are execute the optimistic policy followed by M-step random actions. We just do some random exploration. And once we have that, we can say we can learn everything in terms of polynomial of H, S, O, epsilon -1, alpha -1, the same thing. The only difference is we need to take some A to the M because we do M step revealing. Okay. And as I want to emphasize again, this is like a first line of supervision results for learning from interactions for a rich class of POMDPs. Okay. These are basic guarantees. Yeah. Any questions?
Yeah, quick question. So I know you have like poly dependence on all the parameters, but do you know the exact dependence on at least some of them, like epsilon or alpha and so on?
Epsilon is -2, so it's like statistically optimal.
Okay.
Because of like concentration. And I think the other dependents are like to the power of 4 or 6 or something. We didn't try very hard to like optimize it.
And what about alpha? I'm curious about alpha specifically.
Alpha currently is alpha -2.
I see.
We have a lower bound that says is -1 is necessary. Yeah, it's also not very tight in some sense.
Got it. Okay. Thanks.
Yeah, thanks.
One more question. So the algorithm seems like it's like an extension of what model-based MDP is kind of doing. Essentially, here you are also learning the observation transition matrix as well. So is there something that is like unique about POMDPs, or is the algorithm a kind of an extension of what is?
Yeah, actually, this is a very good question. So, very good question. So basically, we actually have a follow-up work we will talk about later. So this algorithm is completely applicable to fully observable scenario. So basically for MDP, yeah, this is a complete work because you can also just do this MLE thing. But one thing I should probably say a little bit more is in a tabular setting, in the MDP, people haven't talked about this algorithm because this is actually, as in the very beginning, I said that we solve statistical efficiency, but we don't solve the computational efficiency. So there is a caveat about this algorithm. It's actually not computational efficient. So that's why in tabular MDP, people have better way to do it because we observe the states, so we can use dynamic programming based approach. Here, the inefficient part is about this optimistic planning. Remember, we have this confidence set, which is defined by this MLE likelihood. So this is a pretty implicit confidence set. And we need to actually, within this confidence set, we optimize over to find the optimal policy, optimal model and optimal policy. So this is a very sharp way of computing like optimism. And it's not efficiently computable, but it will give you some statistically efficient results. Well, in the MDP, because we observe the states, so there are a lot of further structure we can explore. So we can essentially design some relaxed version of this confidence set so that the confidence set will be independent for each step, and then which makes this computation of the optimistic planning to be computational feasible, and so that we can learn it efficiently.
Okay, sounds good. So I guess essentially this can be thought of as a framework, and then if you have more structure to the problem, you can essentially simplify the computation.
Exactly. Yeah,
Okay.
that's a good point. Yeah.
Thanks.
I have a follow-up question from my previous question. You said alpha power -1 is a statistical lower bound. Can you explain what that means? Because
it's actually
yeah.
That actually just means you have to have some alpha dependence here. Like if it's very close to 0, like you do pay some efficiency.
But what does that mean? Suppose alpha is 0, then if I use exponential number of samples in H or something like that, I can possibly still learn, right?
Actually, why not? Let me show. It's just one slide later. So yeah. So let me just explain this. So we see here we have alpha -1 dependence. We have a to the m dependence. Like so, you may wonder whether those dependencies are necessary. Like whether we can improve over it. So it turns out we say both of them are necessary in this sense. First, we can say for alpha, we can say there exists an undercompleted weakly POMDP, so that alpha requires this many of samples. So it's a minimum of alpha -1 and a to the h. So you're right. If you're happy to pay a to the h, then it's okay.
Okay,
yeah.
Got it.
But if you're not happy to pay a to h, then you have to pay alpha -1. Yeah.
Thanks.
That's a good point. And then also for multi-step thing, it's just because our assumption is weak. Basically, our assumption is kind of like says, as long as there exists an action sequence, so that MSAP observation will weakly revealing the states, then our assumption holds. But which action sequence we don't know. So that's why we have to try a to the m random actions to find that specific action sequence. So if we make the stronger assumptions, we say for some particular action sequence, the observation is like weakly revealing the states, then we don't need to pay this a to the m factor. Okay, this is just assumptions, and we say in our assumption a to the m is necessary. Okay, so these are the results.
One more clarification question.
Yes.
Maybe I missed it, but is the rewards like given, or are you also learning the rewards?
Reward is given. Yeah, as I said,
Okay.
reward function is fixed for observation. So you can think it like, for example, in a target game, the reward is just one fixed part of the image, and we always can directly read from there.
Okay. Okay.
Yeah. I guess we can also learn. We can also handle randomized rewards. It's just okay. It depends on like how you formulate it, but typically like in MDP, learning reward is a lot easier than learning transition. So I think under some reasonable framework, reasonable like formulation, it should be also easily can be handled by our framework. Okay. Finally, I just want to mention something beyond the POMDPs. So far we have always focused on the tabular POMDPs. So there are a couple of work we did after this. One is we can extend this to the multi-agent scenario. So remember, like in the very beginning, we talk about poker, we talk about StarCraft. Those are all the multi-agent scenario. So multi-agent scenario is quite different from single-agent scenario, where we need to deal with like collaboration and competition. And our goal is no longer just find the optimal policy. We want to find the like Nash equilibrium or correlated equilibrium, something like that. So in this recent paper with Qinghua Csaba, we actually studied a model so-called partially observable Markov games. Okay, as I said, you can think it's similar to POMDP, but in each step we have multiple player take actions, and the reward will be distributed to each player, and so different player will have different utilities. So they're greedy they're selfish with respect to their own utilities. And furthermore, in terms of partial observability, we even allow each player to have local observation. So their observation are no longer shared. So you have your observation, I have my observation, so that we don't know each other. So this kind of model will also cover the famous called imperfect information extensive form games, which are the models used like tree structure games is heavily used for poker type of things. While this Markov game is more general, can also handle a lot of can also handle a lot of problems which is like have beyond transition structure beyond the tree structure. So basically, we also need to do two steps. One is identify problem structure. The other one is to have the efficient algorithm. So the problem structure is very similar. So in the POMDP, we say it's weakly revealing. That is, observation reveals something about the states. There, in the Markov games, what we say is as long as the joint observation of all players, that is, we put the information about all observation together. If the joint observation will somehow reveal some information about the states, then this problem becomes tractable. We can learn the Nash equilibrium, we can learn the correlative equilibrium. And we'll just need to slightly change our algorithm. Instead of like in the optimistic MLE step, we have the optimistic planning step, which we find the greedy max, like the best model. Here we will solve something equilibrium. We find some model so that it's good in the it's optimistic in the equilibrium sense. Now once we replace that kind of subroutine, we can actually use similar idea to learn the equilibrium in polynomial number of samples. Okay, this is one work about the multi-agent thing. And the second thing is also, can we just generate beyond the POMDP? For example, beyond tabular POMDP. For example, one thing is like we want to have a continuous observation. We want to have some function approximation. And so essentially in this work, we essentially as a tutorial set, we view OMAE as a very generic framework. So it can apply to a lot of problems, not only partially observable, but also fully observable problems. The most important thing is like first, we can handle the observable POMDP, or it's kind of like similar to weakly revealing POMDPs with continuous observation, so that where we need to use some function approximation. And we can also learn it under a more intrinsic representation, which instead of saying I have some underlying states, and I can like represent the sufficient statistics, use some experiments of the future. So it's more intrinsic representation. It's called predictive state representation. And finally, we can also develop this entire thing under a more general framework, which we identify a general called cell condition. It can handle not only fully observable problem, but also not only the partially observable problem, but also a lot of fully observable problem, like tabular MDP, vector MDP, or low witness rank. Basically, one of the most general model-based class previously in a fully observable setting. So we're saying this OMAE can basically handle a majority of known tractable model-based reinforcement problems under our framework. Okay, I guess this will conclude everything I want to say about the technical part. And any question about so far? This is like a little bit sketchy. I just want to give an overview of what we can do beyond this tabular POMDP thing.
Yes, I have a question. So it's about your algorithm design. In your first step of your algorithm, you need to solve like a max problem, right? A max over theta and max over pi. So this seems to be as hard as the original problem. So how do you efficiently compute this theta and pi?
What is efficient? What is the original problem?
So you want to solve the POMDP, but the first step is
So what you're talking about is planning. Yes, this is harder than planning. Planning means like basically I have the model, I have the model, I have the reward. Basically, I have the transition, I have the emission. I want to find the optimistic policy. So this is called planning, and this is optimistic planning. It's definitely harder than planning. But what we talk about is a learning problem. That is, we don't know the model. So the first step here is basically just a computational thing. It doesn't involve any statistics. So that's why we can just do it. Well, what we care about is in how many samples we can learn it. So this is harder than planning, but easier than learning.
I see. But you still need to enumerate all theta and then probably policy iteration, value iteration to compute the best policy.
You need to do, you can do value iteration in that sense. Yeah. If you enumerate over all the models in the confidence set, that's true.
Okay.
But I just want to emphasize that in this step, like we already collect all the samples, so there's nothing about statistics involved here.
Okay.
Like basically you say for each model in the model class, basically I tell you, I already give you the model. So that's why you don't need to learn a transition emission in that step.
I see. Thank you.
Yeah, thank you. That's a very good question.
May I also ask a question?
Yes.
It's also regarding the confidence set. So first of all, is the confidence set discrete or is it continuous? And then second, when you construct this confidence set, you have this tolerance beta, right? Should this beta also show up in your convergence rate or any complexity analysis?
That's a very good question. So this theta is so this is a confidence set. First, confidence set is a confidence set over models. So in the POMDP setting, models are, as I said, is a transition and emission. So you can think this is a set over class of transition and emission, and most likely it's a continuous set. So basically, I say so my probability is in this interval, in that interval, that kind of thing. And the second thing, what you're asking is about this beta. This beta is actually a statistical confidence. So basically, this thing is tells you something about the uniform concentration over all the models. So it will be in general some log covering number over the models. So in this case, in the POMDP setting, because the model is just transition and emission, so model can be, the complexity is upper bounded by, the log covering number is upper bounded by some polynomial of observation, number of observation and number of states. So it's kind of like implicitly appeared in this polynomial of the state and action observation here. But in general, yes, if you do some like generic function approximation, then it will depend on the covering number or even bracketing number of this model class, and it will show up in the sample complexity.
I see. Thank you.
Thank you. That's a very good question.
So I have a follow-up question. So
yes.
So since your theta set is continuous, how do you solve the planning problem?
Oh, this is like, as I said, this is, I'm not regarding any computation problem. Like I just think computation is, I have infinite, okay. So tricky answer is I just assume I have infinite computation power. So I can just do this step. So this is like pure statistics. But if you really ask me, I think although it's continuous, but it's not like differ by some epsilon. I think there's some relation between like a nearby transition emission, so that you have some way to solve it. But I think you still require some exponential time, but you don't need infinite time.
I see. Thank you.
Yeah. 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 As I just want to mention it again, since it been raised a lot about the computation issue. I mentioned it in the very beginning. The computation issue is not because our algorithm is just also intrinsically there for learning POMDP, where there's some computational hardness, and it's not very clear like whether just assuming weakly revealing is enough to avoid a computational bottleneck. If you ask me to guess, I feel probably it's not enough. Like we need more structure to avoid a computational bottleneck.
I see. Thank you.
Thank you.
Okay. I have a question.
Yeah, yes.
Sorry. So you mentioned this is like model based, but then are you saying that model free kind of approaches are kind of hopeless in this regard, or can you maybe approximate it by some Markovian policies and then work under some approximation and then make that work as well? Or
I think model-based, a model-free approach would work under some other assumptions, like probably under a subset of this weakly revealing thing, because this weakly revealing is like a very weak. Essentially, the condition is very weak. Essentially, it just says it needs to tell you a little bit of information about states. So I'm okay with like I just have when I infer about underlying states, I'm okay with like I have a 60% on this states and 40% probability on this states. So this kind of thing is allowed in our model. But I think model free would work more if we are more deterministic. For example, based on history, I can fairly confidently tell I'm in this states or not. And also more importantly, I think if we can use some short history to directly tell like what is the current state, what is the next state. So in kind of those scenarios, so we actually have another paper which is called decodable POMDP, multi-step decodable POMDP, where it basically says as long as you have used like a 3-step or 4-step of history, you can decode what is underlying states. So those models are actually much easier than like much smaller than the model I talk about in this talk. And there you can use some more model-free algorithm. But in general, like this big class of POMDP, where I said you cannot just really avoid this problem of optimal policy or optimal value, always depends on the entire history, where basically with this makes model-free type of algorithm really difficult to deal with this problem.
Okay, yeah, that makes sense. Thank you.
Thank you. Okay, I will just quickly summarize, and we can also answer more questions. So as I said, this I hope you kind of convinced this talk kind of provide the first line of sample efficient results for learning from interactions in large class of partially observable problems. So we just introduced one very simple algorithm, that is optimism with MLE, and we can deal with first is weakly revealing POMDPs, a very large class of POMDPs. We can even deal with multi-agent version, that is weakly revealing partially observable Markov games. And also we can handle some continuous observations and more intrinsic representation like PSRs, or even beyond that kind of thing. If you ask me about some future directions, I would say, yeah, definitely there are a lot of more interesting directions in partially observable thing. And I would say even those are just first line of results, it just mark the beginning. So one thing is like, can we define even richer class of tractable partially observable problems, like beyond this like weakly revealing thing? And it's just one sufficient condition. We might have more general results. And second thing, we haven't addressed is computation efficient. What are sufficient conditions for computation efficient learning of partially observable problems? That's another question. I guess I haven't read it. It's also like some sharp dependency observation and mission things is also like worth a lot more investigation. Okay, I guess that concludes my talk. Thank you.
Let's thank Chi. So Sushil pointed out earlier in the chat that the title is catchy, and despite being catchy, he did answer the question about when POMDPs are not scary. So that's a very nice talk. And I also want to thank Chi especially for doing this despite his current health issues. So thanks again for the talk.
Thank you.